Okay, hello everyone. I am Poorna Shyamsundar, 2019-23 from 2019-23 batch. My roll number is CS19B049. So, welcome to the video on the CSD project. Like this video is made to help students understand what to do in the upcoming CSD project, like whatever you're going to do. You'll find that this project would be something newer than what you did, whatever projects that you did earlier, because this will contain everything from start to the end. Like as we move on, like you'll understand that whatever you learned all these 3 years, so this will be 4th year. So we'll be applying those here to build a computer actually from start to end. The course is like computer system design. So we'll be designing a system, an end-to-end system, both hardware and software from start to end. So this video should help to understand the project and what is the goal of the project and what to do, like what is that you have to achieve at final, like what is the result, what is the outcome that you can expect, like what is the outcome that sir is expecting from you. So I think this will give you the understanding, so with which you can start the project and then successfully complete it, like more than what we did in the previous year. So this is the first video, like the introduction video. So you'll be listening, or like I'll be talking about the complete overview of the project, the parts of the project, how the project moves on throughout the semester, and what are the different components in the project, and like what to, like finally, like the expectation from the project. So before we move on, like the goal of the project, like we said, so building an end-to-end computer. So let me just seek to the part of the video. So this is the demonstration of the video, like demonstration video of our project, like whatever we did in the ARM team, the team 2 ARM team from my batch. So this is the demonstration. So what you can expect is that at the end of the semester, you will be designing something like this, something similar to this, or something at a larger scale also. So let me just go back to go. Okay, so this is, you can see, right? So this is the final setup that you will be achieving. Though you will be provided with this display. This is a FPGA board. It's a programmable board. You can design your own processor and then implement that processor in this board. This is a keyboard provided by, like everything will be provided by Dr. Jaynarayan, and just have to use them. So at the end of the day, you will have a processor like this, a keyboard, a display, and power cables. That's it. So, and then you'll be doing something like this. So if you see here, so it's just a computer. You'll be developing this computer. So whatever you see here, the display, the black and white screen, everything, you'll be programming everything. You will be driving the display actually through the HDMI port. You will program the keyboard, like you will receive the input from the keyboard, process it, like you'll be building the entire system, that whatever you use. Like at the end of the day, you have 3 components, just 3 components: the display, keyboard, and processor. No other laptops or no other things. So you will understand, like as you go on, that there are many hacks that people did to simulate this behavior, but that's not the right way of doing it, or that is not the expected way of doing it. At the end of the day, there should be only 3 components that works. Like there should not be any external support. Like you don't have, like you can't drive the display from your laptop, or you can take the keyboard input to the laptop, process it, send back to the processor, and then do that. Everything should be within these 3 components only. So that's the only, then will it be a independent computer. It's not like just a computer. You have to build an independent computer that is not dependent on any other thing, any other support from your laptops or the computer systems. So a laptop or a computer from scratch, that's what you have to build. So regarding the capabilities of the computer, we can see something like this. So
And then
So we
so
built
we
a
can
snake
see
game. So that's the
this
snake.
game is loaded. So just to play the game, we can
Snake game, which
just
you
use
can play
WAS these four
four keys.
buttons, and then you can just you know uh, operate that operate the snake.
So this is snake game. So this is the final, what we can say, the achievement, like something uh, like a test or something like that. So how do you know that the computer is working perfectly or something? How do you demonstrate the capabilities of the computer? You can build something like this, a game, or you can actually also build some complex programs, complex animations with just this black and white screen. So to demonstrate the capabilities. So at the end of the day, you'll be expecting to do something like this. Uh, uh, like you may not completely understand now, but as we go on, we may understand like what is expected or what is that you are going to do. So like you got the idea, right? So I'll be sharing these slides. You can watch the entire video. It's uploaded in YouTube. You can get from this YouTube video the slides. So now let's move on to the actual project. Like,
Hello.
okay, so the project is a 16-member team project. So it will be roughly divided into 3 or 4 teams. I have requested sir to reduce the team size, though 16 is a big number. Uh, if we question whether the each individual will be able to do and complex enough work for a semester, so I think 16 would be large at a large like overestimate for this particular project. It can reduce, like 3 or 4 members can be removed, and then maybe 12 would be the 12 or 10 would be the ideal size for the team. So whatever like like according to this class strength and everything, I think we can divide the teams. So but we did a 16-member team project. So the project is completely divided into 7 components. So I'm assuming that the project is already introduced to you uh, by sir before you watch this video. So assuming that, so as sir would have already told you, the project is of 7 components. Uh, so the OS and processor design have 3-member teams each, and the rest of the components will have 2 members each. So if you see the 7 components of the project, like first one is the high-level language design. So whatever you have done in your compiler course, we designed a language, built a compiler and a translator, and then translated to some machine code, some assembly code. My team converted that to MIPS code and then used QtStream to run the final output. So uh, I came to know that you didn't do that project. You didn't actually build a language and then design a compiler for that, but there are some weekly assessments or something. So that would be a disadvantage for you. Like this was an advantage for us. So since we already built a compiler, so we know beforehand what to do. Like we could plan that, and it was not something new uh, to do in this project again. So, but also it would be the same. Like it's good that you didn't have to do the repetition work. So when we did the project, the compiler team and the translator team and also the high-level language team didn't have that much work because we adapted whatever we did in the compiler course. But you will have to do from scratch because you didn't do anything. So these are the 7 parts. So if we go to first is the high-level language design. So in the high-level language design part, you'll be designing a language of your own choice, your own creation. You could say like ours was CNP language, C and Python combined CNP. So we designed a language that looks similar to C and Python. So we took some constructs from C and some constructs from Python, combined them together and designed a new language. Like the variables and declarations are similar to C. So in C, you declare a variable like int a comma b or something like that. We adapted the same. So even in our language, if you want to declare some variable, like it would be int a or char c or string. Like there is no string in C, but there is string in Python. But we have strings in our language. So string str, and like we adapted Python. Like we see we have printf, something that works like we have this thing percentage d and percentages. But in our language, it's similar to Python. If you want to print a variable, let's say an integer a, in C you would be doing like printf %d comma a. But in Python, you'll just say print a. So we adapted that. In our language, if you want to print some variable, so the type will be inferred. So whatever the variable has a type, fixed type, static type variable, that will be adapted. That will be inferred from the statement, and then accordingly, whether we have to display the decimal value or whether it is a character or a string, everything will be automatically inferred and then printed. So we use that print statement. So similarly, you can use whatever you want. You can design your own language. So I will go through the design part one by one. I in the next few slides. So and the next one is the compiler. So once you have designed a language, you decided like what the language looks like. You can also write some sample programs. For example, you could just write a Fibonacci program. So again, the complexity of the language should be enough for you to write an OS in that particular language. So when you write OS, you require functions, you require recursions, you require arrays, pointers, if possible, even struct variables like union structs in C, something like that. So you may require these kind of capabilities, multi-dimensional arrays, character arrays. So all these will be required when you write an OS. So what I say is that you talk with all the teams, like you talk with the OS team, like what are the capabilities that they need, and then accordingly the high-level language design team should design such a language so that whatever the OS team intends to implement or write the code at the highest level possible, the language should support them. And also discuss with the compiler whether it is compilable, easily compilable, and also if it is difficult, then we have to discuss and then bring out a basic version so that it can both be used by the OS and it is easy to compile, write a compiler for that, and also translation and also assembling. So this project will not, because it's a 16-member team, it's just that 2 members will do high-level language design. Doesn't mean that high-level language design is not a team. So the 16-member is the team. So what that means is that say there is coupling between adjacent teams, even with all the other teams also. If you see, the first 5 components is about the software part. The rest 2 is the hardware part. So when someone decides something about compiler, it's going to affect the high-level language, virtual machine translator part team, assembler team, and OS team. So even though the teams are divided into like there are components, you have to communicate with each and every team. So the team leader should take care of this and then communicate with each and every other component, because it's highly coupled and you cannot escape communication from other team. So you might end up even at some points where the compiler team will come to the assembler and then change something, and then assembler team will go to compilers and change something like that. So you may also need to work on some components collaboratively. So don't draw a strict line on like this is not my work or something like that. Just try to be open to any kind of intervention from others, and also intervene with other teams also and try to build that. So the compiler part is the compiler generation. Like you didn't do this compiler thing, so we may not be able to quickly grasp that. But a compiler would be something like translating the high-level language to a 3-address code. So if some statement is like this, in the high-level language, the one of the line is sum equals to a plus b plus c. So that's a high-level statement. Like how do you compile that? When you compile that, you'll be converting it to a 3-address code. A smaller set of is a simpler, much simpler statements. So you would say, let t1 equals to a plus b, t2 equals to t1 plus c, sum equals to t2. So you'll be using temporary variables. You'll be introducing temporary variables other than the variables that are introduced by the user or the programmer, and then you will make sure that every instruction in the temporary code, the 3-address code, is in this form: a equals to b plus c or a equals to b minus c, if a equals to a double equals to b, something like that. So you would have learned these all things in this compiler course. So you will be applying everything like that. you will be using Lex and Yak. That's what we did for the compiler project and also the CSE project when we were designing the compiler. So you can use your own. There are, I think, many other things, but Lex and Yak should be enough and powerful enough and also easy to use. So you can use that. And the translation. So translation is that converting that particular what is called TLS code to machine assembly code. So so that here where the register allocation comes and also stack pointers, jump instructions, everything, like how do you convert A equals to B plus C? So you should first know where is B's location. So you'll be writing load R1 with the value of B, load R2 with the value of C, add R3, R1, R2, and store R3 in A. So A equals to B plus C. So that particular one line, the temporary code translator, you'll be translating it to these four assembly instructions. So what is that assembly language? Again, that's again new. Like you have to design your own instruction set architecture. So which means that MIPS has MIPS architecture. You can refer MIPS or x86. So like that, you'll be designing your own assembly language. You can name it anything if you want to just name it. Like if some, for example, you'll be designing a architecture where the add instructions like this: add R1, R2, R3, which means that R2 and R3 will be added and be stored in R1. You can design your own architecture like R2 or like R1 equals to R1 add R2 R3, something like that. You can design whatever language you want, as long as you are sure how to assemble it again, because the next part is assembler part. What you will be doing is you'll be translating the 3-letters code to machine code. So, and then from that, it's like a 3-letters code to assembly code. And then from that assembly code, you'll be translating it to machine code. Machine code is nothing but 0 ones. So like I think you could do a 32-bit architecture. 32-bit architecture should be sufficient for whatever goals that you plan to. More than that, it's not near. And also it is easy in 32 bits because the integer values and integer values is 4 bytes, so you can easily fit. When you compile, when you try to convert immediate values, I think 32-bit should be fine as per the like regular things. Or you can do 40-bit also, 42, whatever number you want. You can design your own ISA architecture. But again, this ISA should be based on some architecture that is your team. So like I told, like we have 3 teams, 3 16-member teams. So the difference between each team is that the architecture on which they should base. Like our team was ARM architecture, so the ISA is adapted from ARM, so the instructions will look similar to ARM. So some version of ARM, there are many versions of ARM instructions. There are thumb instructions, there are 64-bit versions. Something you can adapt from that particular language, ARM, like a basis, like a base, and then adapt your own architecture similar to that. Again, the other team was RISC-V and the other team was MIPS. So everything are RISC-based architectures only. So fixed length, load store type of architecture. So it should be easy to write both the assembly language and then to assemble them. So once you design this pipeline, so once given a high-level program, which is according to the specifications designed by the high-level team, you should be able to compile it, convert it to 3-letters code, and then translate it. So here again, virtual machine and translator. What is a virtual machine? A translator. We'll discuss that later. So for now, what you can do is that you'll be translating the 3-letters code to what do we call that? With assembly language, assembly code. From the assembly code, using assembler, you'll be converting it to machine language. So once you have this pipeline, given a program, at the end of the pipeline, you will be getting sequence of zeros and ones. Once you have this, on top of this, you'll be writing an OS. So the high-level program that will be going through this 4-stage pipeline, like high-level language design, compiler, virtual translator, and assembler, will be the OS. So the OS is the one that will be going through this pipeline. So what do you design in an OS? So OS is nothing but, for now, what you can understand is whatever you see whatever you intend to run finally on the computer, on the display, what should be displayed, what is the computation that should happen behind the processor, like in the processor, or what is that you want to read from the keyboard, what is the thing that you want to do with the keystrokes presses, like what do you want to do them, how do you want to display, what is the uh, uh, like how do you program the display to work, how do you intend, so everything, whatever you intend to show in the final presentation, that's what is OS basically. OS is some, like it can be any other thing, but for now you can think of it as a one big program that finally is going to run on the processor. So when you switch on the computer, so what is that you want to, what is the first instruction that you want to run, the second instruction, third instruction, that's what is OS basically. Now for now you can, we'll expand that idea later, but for now that's the OS. You can, you don't be what do you call that, blinded by the like what we say, by thought that voice is something that is written in the high level language design. No, there are parts of voice which are written in the high level language. So when you want to write the system call for print, let's say that you designed a snake game, and that's what's snake, we designed a snake game. So to display the snake, you thought like, I want to use a print function. Given a character, it will just print at that particular location. I say print 0000, which means that a snake of 0000 will be printed, a star 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 will be printed on the display in the next line. So you will be required to write that function print. You till now what you do is like, when you want to write, you'll just include hashtag include stdio.h and then use printf, or Python use print, or you use like scan, everything just like that. But there is nothing like that, because the language you design, there are no libraries. So you have to design your own system calls. Like you have to write your own print function, you have to write your own scan function, you have to write your own process fork functions. You know, whatever you learned in OS, like whatever things that the system calls file management. There is no file management that we implemented, but you get the idea. You have to write all the program, all the functions, those which you use till now for granted. You just assume that it works, somebody written, you just be using that to develop software. But here, it's not given. You have to write your own print functions, everything. So when you start writing those print functions, you'll realize that I cannot implement this print function solely by using the high level language. You will realize that there will be some part of the OS which should be written in assembly language. So you should not think that OS is not the final program, big program, but OS is the final machine code, is what we call this OS. So you understand that. So whatever you write, the CNP program, like ours is OS.cnp, the file is OS.cnp. So whatever you write, that is not the OS. That is some part of the OS. When you compile it, go through the pipeline, you will see additional assembly languages, assembly language instructions introduced into this particular machine code. So this is what, like, it may seem trivial or you may not understand right now, but this is what we came to the realization after doing the project, which is something we didn't know at first. It might help, like when you start project, you might understand all these, like what I'm telling right now, may not be able to vision like why is this important, why is the fact that voice is the mission code, not the high level language. Like it may not seem trivial to you now, but when you come back to this video again, like I request that please like every like 1 month, like or some progress you made in the project, come back to this video and see again. You'll understand, you'll have better understand, and you may find some pointers which you are trying to find on your own. So that's the OS part. This is software part. So we have a program which is the OS, designed according to the specifications, high level language design, and then you went to through the pipeline, compiler, virtual machine, and assembler, and then you got zeros and ones. A very long list of very big sequence of zeros and ones. Ours was, I think, 36 KB. So there are 36 KB, 36 into 2 power 10 into 8. So those many zeros and ones is what we got at last. So our OS is that long, 36 KB size OS. So you take this 36 KB OS, so which is designed according to your own architecture. So ISA is the bridge between software and hardware. So you got this very long list of zeros and ones, and then the goal is to, assuming that these zeros and ones are designed following the standards of the ISA, you have to design a processor that will process these zeros and ones. So you understood, right? So whatever you got the machine code, you design a processor that will execute that machine code as per the ISA specifications. So that is the processor design. So the two major things in this project, which are very, very important, is the processor design base. So on the OS, these two are the major. That's why they have three members each. And then system integration, where display and keyboard will come. So the processor design part is the difficult part. You may find even at some point it's impossible to build something like a processor layout to go further on. So make sure that you put utmost effort on processor design. I even request system integration team, the 2 members. I think 3 would not be enough. 5 members should sit on the processor and start working on it. Because once the processor works, only then whatever you do, like the compiler, translator, and assembler will matter. So no matter how high level language, what kind of like how many constructs you build, what a good compiler, like you can build the amazing like a very large or very powerful compiler, translator, and assembler, and if the processor is not able to process that machine code, you cannot demonstrate anything. It goes, we cannot even find a way to demonstrate the power of the compiler. You understand that? So the thing is that even if one of these components fail, and even if they say the processor team didn't work much and then they couldn't design a working processor. So no matter like, so the other teams may say like we built an extraordinary compiler that can compile any kind of code with very good error recognition and then ambiguity elimination, everything. Maybe compiler is very intelligent enough for you to even correct its own code and then compile it without errors. But you cannot demonstrate that power without actually compiling a thing and then running it. So when you understand, like if the compiler teams, maybe for some reason the compiler team completes their work faster, like before any other team, then the compiler team should switch to other whatever is lagging to that team and then start working there, because you completed the compiler, but it's not going to be used. You cannot demonstrate the power. It's like it's a waste. So each and every component from the start to the 1 to 7 should work perfectly. So this is where I suggest like you go through the parallel approach. Like this is what I follow in every project, and also I suggest everyone to that, is that you divide the project into like eventually every project is some pipeline, some graph with start nodes and end nodes. There are no cycles, of course, and it will go parallelly because there is a critical path for that tree graph. So what I say is that don't do a DFS. Instead, do a BFS on multiple nodes, starting at multiple nodes. But what I mean is that you don't start with the compiler. Like if suppose I say that all 60 members should work on one project or one thing. So you don't go, all the 60 members will start working on high level language design, complete it. All the 60 will go to compiler. Somehow they will divide the work and then compile the compiler. And then 16 will come to virtual machine, the 16 will come to the assembler. That is not going to work, because you will not know the problems of the high level language design unless you use that in OS. So what I suggest is that build incrementally, each part separately. So you do a little work in high level language. Let compiler team do a little work, translator do a little work, assembler do a little work, OS do a little work, processor system integration. So let the work go parallelly, each level, and then So it should be incremental. Like what you can, for example, by incremental, like I'll give an example, like let the high level language design team declare that the assignment operations will go like this: a equals to b plus c. That is what they designed. That's a trivial design and a straightforward design, but still they designed a equals to b plus c is what we are going to use in our language. Let you build build compiler strong enough to parse only that particular type of instructions: a equals b plus c, e equals to f plus g. So the compiler will do only that work. So the compiler is capable of only compiling a equals to b plus c. You build that compiler from start to end. Let it compile and convert into a 3 address code. And then you build the translator that will translate only that particular instruction, which is a equals to b plus c, that 3 address code. And you build the assembler that's going to assemble only those kind of assembly languages. So we saw like a equals to b plus c will get translated to 1 3 address code and two codes: t1 equals to b plus c, a equals to t1. That's what is going to get translated in my, at least whatever we designed. And then t1 equals to a plus b will get transferred, like t1 equals to b plus c will get assembled, like it will be converted to assembly language of 4 or 5 instructions, 4 or 5 instructions: an add instruction, a store instruction, a load instruction. That's it. So you build assembler that is going to assemble only these 4 instructions: add, load, store. You make sure that the assembly is at least capable enough of assembling these 3 assembly code. And then in the OS, again, you make sure the processor is capable enough of computing only these 3 instructions. Like just write the processor data path for load, design the data path only for add, and then let the system integration team just something like that. So make sure that you build in this manner. So after adding each and everything, make the complexity distributive and then increase the complexity in each part step by step. That's what I would suggest. That's what worked. You can also try that. So coming to each part of that, so I request everyone, all the teams, like all the members of the team, irrespective of their component, to watch the video entirely. And the first one is the high-level language design. So again, I said, like whatever I said is same thing. Design your own language, something similar to C, Python, JavaScript, Java, whatever you wish. So it should be simple enough to compile down to an ISA. So when you design some very complex construct, like something like ternary operator, like with a question mark, like what is the ternary operator? I think what we use in C, A W equals to B, question mark 1, colon 0, like that. Some complex things you design, but you should be able to also compile that. So should be like a high level design will imagine in an architect level, and then the compiler team will not be able to achieve that. Don't make sure like that. Converse with every team, and then should be simple enough to compile down to an ISA, complex enough to write an OS. So these are the 2 things that the high level language design team should keep in mind. So whatever you construct you design in your language, make sure that you are capable of, first of all, compiling that, and then also it is capable of being for an OS. So the language is capable that we can write an OS in that language. And these are some minimum things that should support, like whatever we did. As for to write an OS, these are mandatory, at least. The data types int and char. So the language should support integer and character variables, multi-dimensional arrays, at least multi-dimensional integer arrays, if not character arrays or string arrays, pointers and addresses. So the ampersand operator, make sure you have that, and also pointers. Once you have multi-dimensional arrays, it means that one or the other way you're using pointers or references. So pointers is more basic. Use that. Don't go with the fancy things. Just like you will understand, even if you go some fancier way of addressing or some fancier way of passing arguments, you will soon realize that it's difficult to achieve that. You'll come back to again. All the way you'll be searching, and then finally you'll be coming back to these only. At least I hope. I don't hope that, but I think that that is what going to happen. That's what happened to us actually. conditional and loops, like conditional statements like if, elif. So again, we used, instead of else if, we used elif for sequential if statements from Python instead of from C. Something you can just invent your own. You can write if not, else, or something like that. You can design your own things, whatever you wish. You can design that. Then use the conditions and loops also. At least basic for loop should be there. If not while and do while, at least for. I think if you have for, you can use it as while and also do while. That doesn't matter. And recursive functions. So again, function calling is important. Without function calling, you cannot write an OS. OS has to be function calling. So the thing is that when what do you say? When we got this compiler project in CD lab, many people didn't include recursive functions or function calling as one of their constructs, or at least functions itself. Like once you design functions, you have to recursive functions. They didn't include that. Many people didn't. I think only 2-3 teams included recursive functions in their things, and then they only I think partially achieve that. But here it is mandatory. You have to have recursive functions. You have to have very deep nested functions. You should be able to call functions and functions and functions. I think it's basic, but you will realize that it's mandatory. It's basic here, but actually recursive functions is mandatory. So design a language like that in these lines. Okay, and also so this is a introductory video. I'm not going through the code. At least I will go through the code. I just show the code, but I'm intending to make separate videos for separate components also in depth, showing more of the code and then explaining more of it. But that should not be required for you unless you are stuck at some point and you want to have a look at what we did. But this video should be enough. Like whatever knowledge that we gained through the project, I think this video has it. You don't have to go through those individual videos unless you are completely stuck and you don't know what to do. Okay. So this is the high-level language design. I'll just show you the what do you say, the OS code, so you know what kind of constructs I'm talking about. So this is the software part, the front end, whatever you see, the 5 components. High-level language design. I think it's not code; it's just design part. Leave that. Compiler, translator, and assembler, and OS. So all these files are here. You can see these things, and so the extension for our OS is .c and p, but I made the extension to .c so that the syntax highlighting, so the vim will highlight the syntax. So you can see this is the, so when you see this code, like this is some 1600 line code. Whatever you see this is the language that we designed. So when you see this photo, so elif, I told you, right? The condition statements are, we use elif instead of else if. So print string. So what the print string function will take the variable and the starting point and the ending point. These are the sub functions. You may not understand now, but the OS designers should understand like what we did. So it's like I told you, while loop, an infinite while loop. You can just write for semicolon, semicolon, it will work. So whatever you see here, if break statement, break and continue are also useful. Make sure to incorporate them in your language design. So this is this code for the snake game. So this is the OS. So a big program. You have one main function. So when you say that PID equals to 1, is this the first instruction that is going to execute when you start the computer? No, there are many instructions before this. Those are in assembly code. You will not see here. Once you go to the assembly part, you will see we appended some assembly code before the main function and some code after the entire program. So that is also OS only. It's just that you can't write that particular part of OS in high level language. That's it. So PID equals to 1. So there are global variables also. We see these are global variables. These are basically the OS variables. So this particular file is the OS, and these are the variables that the OS stores in its own stack. So and so string length function. So we know in C we have strlen function, but in our language there is no strlen function. I wrote my own strlen function. So I was part of the OS team designing the OS. So many of these code I have written. So strlen you have to write your own code. You have this infinite for loop break statement. So unless in C you have, like, you can, after an if statement you can have either one statement, or like this a block of statements. But in our language you can't have just like something like that. If should be followed by open and close parenthesis, it should definitely be followed by a block, not just a statement. So that's a language decision that we took. So you can design your own language. So it may seem almost like C. If you see, you'll not at all find different, any different from C, but it is different from C. So this thing map start like display function. So it will take as input a character array. Like what is that thing you have to display? That array, the size of that array. Again, C, right? In C++ you'll have vectors, but we don't have any functions like that. So we have to pass both the pointer to the array and the size of that array, so that you don't exceed addressing the array. And what is the line? In which line do you want this particular array to get printed? I'm starting from which column? I think there are 40 lines, 40 not 30 lines. So the display that you see here, so here whatever you see, it's 30 lines, 40 characters, 30 into 40. But here you see it's I think 80, I think it's okay. It's 22 lines, and the number of columns is I think some 40 or 50, 60, something like that. So that's also you can design, like you can set upon like what is the resolution of the display, like what is the font that you want to display, what kind of font you want to display. We'll soon learn all those things. So display, this is a display function. So whatever character you want to write, you're writing it to some particular location of the memory. So if you see here, there is a variable called memory. So that directly addresses to the memory. The memory is initialized with 0, which means that it is pointing to the first byte. So it's character array, which means that we can address through bytes. So this particular memory variable is pointing to the first byte of the 240 KB memory. So our memory size is 240 KB. Again, I'm telling that 240 KB, you can achieve 240 KB if you use VRAM in the process design in Prado. I will talk that about in process design. So you will be, the memory size is 240 KB. The OS size, as I told you, 36 KB. Like you can assume it's 40 KB. So the remaining 200 KB, some part of it is for memory, some part is for the fonts, whatever you want to display, and some part is the stack heap for like divided for the separate process to run simultaneously. We also implemented process sharing. So at max, along with the OS, the computer can run 5 processes at a time. So the 5 processors are scheduled according to what we call round robin schedule. Yes. So for every half a second, process which happens. So if there are 2 processes, let's say running, at max you can run 4 processes, but let's say there are 2 processes currently running. So if, for example, like the first process will get half a second to run, and after half a second, this process will go background, OS will come into foreground, and it will switch the process to process 2 from P1 to P2, and OS will go back, and P2 will run. P2 will run for half a second, P1 will run for half a second. It will keep on doing at least like it will keep on going till the point where one of the process ends, and then only one process will keep on working. So even if there is only one process running, for every half a second, the voice will come. That's a dumb decision to do, but we did because it's easy. It was easier for us to. It's a much more generalized case. So what happens is that every half an hour, for every half a second, the OS comes. That's for sure. The OS will come to play. Whatever process will go background, OS will come. And if it is the only process that is running, then the OS will return and schedule the same process again. But if there are any other process, if you go to the next process, it's like a counter 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, like that. If there are no 2, 3, 4, again it will come back to 1 only. So that's how we design. So you'll also design like this one. So when the process switches, there is malloc function that we implemented. The malloc function is not implemented anywhere here. The malloc function is implemented at the translator level. So the OS team will be required to write the OS in this language, in the, whatever you see, this 1600 lines code. This code, and also the OS team will be writing few functions like inbuilt functions like malloc in temporary code, and also you will see few functions like ASM. This particular function ASM is written at assembly level. So what does this function take? It takes load R11 ID. That's like keeping aside what that means. The translation, like what is the final assembly code that this particular line is going to get translated, that logic will not be here. It will be in the assembler part, not assembler, translator part, not translator, translator part. So the OS team should go there, should know how to include their code in the translator's code. So as I said, you have to, it's very highly interdependent. You have to go back and then search everything. That's it. So I think the video is getting too long, but I hope you will like you will be watching in 2x or something like that. It should be fine. And I think once you get stuck, this you may come back again to watch the video. You may ignore it first. So these are the 7 components of the project, and then high-level language design logo, like talked about this. So this is the sample of high-level language. So this is how a high-level language decision would be made. So what is the addressing of an array? Simple, just like C. That's what they designed. We have language design, we design. So that's what this is simple. So high-level language design may seem simple. So I request when I think they'll be completing their work much earlier than the complete project. So I request the high-level team to go to the compiler team and then work with them, because compiler is going to take more time. It's harder, at least for you. It's going to be even more harder than what it is for us, because we didn't do the compiler project. We have no experience about that. So I request high-level team to go to the compiler team and then work on that. So this is how a high-level language design would look like. And coming back to the next thing is compiler design. So a compiler in any desired language. So you can build a compiler in any language. We used Lex and React, which forced us to build the compiler in C or C++. We chose C++. So based on the tools that you pick, you will have to write your own compiler in some language. Make sure that your compiler has no conflicts. The language design is made such that there are no conflicts. You would have learned about shift-reduce conflicts, shift-shift conflicts, reduce-reduce conflicts. So there should be no conflicts like that. And when you compile it, and the goal is, again, the goal of a compiler is to compile that to a 3-address code, custom 3-address code. That's the goal of a compiler. Again, that's what, right? That's the goal of the compiler, compile it to a 3-address code. So I'll show you the compiler code. So the compiler is this is the compiler. Like first of all, I'll show the Lex file. So these are the tokens. Like these are what do we call these names? There is some name for this type of variables. Variables for which you cannot use as variable names. Break, you cannot use break as a variable name, because break is inbuilt. I don't remember the exact term that we refer to these kind of strings, but this is the for, written for, a for token, like a tokenization you would have done in your at least CD lab. If not the project, you would have done in your CD lab. So digit, how will you prefer digit? Anything between 0 to 9 is a digit. What is digits? One or more number of digits is the digits. A letter can be anything from lowercase a to z or uppercase a to z or underscore. An integer can be represented like this. It's a group of digits, or it will be followed with a plus or minus sign, like in the front. and then digits, followed by an optional E raised to some power plus or some power digits again. So these are the standard. I don't remember the name that we use to refer these kind of translations, but these are standard. Like this is we borrowed this right from these two links. I'll show you. I open these two links and show you. Borrowed from that. We did the same thing for compile project, but that doesn't mean it's not like copying or anything. You're free to use this. These are standard things. You can use these translations. Many things are straightforward. You don't have to like simple code. This simple plus plus, or this is a lexer. So and we have parser. So this parser some 1200 lines of code. So this main function, it takes the file as input. It will call the parse function, and unless you get an error, it will keep on parsing, and then writing to a table, writing to it code, and then translating it to some what do we call the address code. And if there is any error, it will output the error. So the starting point, like what is the starting point we have here? Something start with begin. Begin is the begin. So whatever code you write, any file, it's begin. It's completely begin. So what does begin consist of? It's a sequence of blocks. It's a block. Begin, nothing but translates to blocks. So what does blocks do? Blocks will have attribute followed by blocks, or function prefix followed by blocks, or it can be empty. I think this is what you have learned in compiler, how to design. So blocks, again, what is an attribute? I don't know why I named it as attribute. I don't remember that, but attribute is something like this, a statement, a type name means int char or something like that. Stars, how many stars? Like star, 1 star, 2 star, 3 star, like the pointer, right? Pointer addressing mode, identifier, a variable name. A function prefix is something like this, a function declaration. So this is the entire grammar. If I show you the entire thing, you may get confused, but what at least you can follow these links. So this is ANSI C. If you are aware of ANSI C language, so this is the official. This is the Lex file for ANSI C. So for constant, I have put string from somewhere here. I don't remember where I did that. Yes, integer E. No, not this. But yes, somewhere here, string. So you could search like how to write the grammar for string, lexer for identifying strings, for tokenizing strings. And this is the corresponding grammar. So you can it may seem similar to what we did, but this is too much. Like it's for complete language. We don't decode this. You can just have an idea of what it looks like. So this thing I adapted from here: multiplicative expression, additive expression, shift expression. I didn't use this. There are no shift operations in our language. Relational expression, we took this. Equality expression, we took this. And exclusive or we didn't take this. Inclusive or no. Logical and logical or yes. Conditional expression, like this is not how our conditional expression looks like. We didn't take assignment expression. It's completely different. Assignment operator may be similar. And expression is also different. So you can just have an idea like how does this grammar looks like. You can I attach these two links here, right? You can follow that. So that's the compiler design part. So let me just show you the working of the compiler. after I think I should make this video as 2 parts. I'll end the video with the compiler and then come back again with the translator. Okay. So before doing this video, I made a sample code, sample.cnp. This is some sample code. So in whatever specification that we designed, this sample code. Like I declare 2 global variables x and y. There is some function sum that returns a plus b. There is main function, and I'm just assigning I equals to 10, j equals to 20, k equals to sum of I comma j, and then returning 0. Main returns 0. Again, it is mandatory for every function to return some value, some boundary value. There is no void. There is no void. You have to return it. Like that's what we decided because it was easy for us to build the compiler. I don't remember exactly what was the problem with doing void, but we definitely had a problem with void. Okay. So once we got sample.cnp, I'm going to generate the temporary code for let's see how is temporary code for this particular thing looks like. 1 minute. Let me not just translate it, just compile it. Like whatever we saw is that I'm first compiling it, converting it into a TLS code, and then I'm calling the translate function. So the translate function will translate that to an assembly language. But I'm not doing that right now. I'm just compiling, only compiling, no translation. Make it again. So this is how you use our compiler. You will call the /gentime. Gentime is the executable, and you'll pass the file. Once you do, this is the compilation that happened. At the end of the day, what you see is the symbol table. So it's not just symbol table; it's the entire thing. Like the entire file is converted. So the task of the compiler, you can this is the goal of the compiler. So what I envision is that each and every component has some goal that it has to achieve. So the goal that compiler achieves is this particular table. So if you get your compiler to print something like this, then the compiler job is done. So what it does is it will compile all the attributes. So it compiles, it got to know that there are 2 attributes x and y. As I showed, there are the global variables x and y. What are their types? Integer. That's what it inferred. This information is what you have to store inside x, y. You got that. Are there any constants in the entire code? There are no constants. So constants was actually used for, let me see. What is that? I think string constants. Yes, the string constants will be visible here. What are string constants? You see, those will be visible here. And what are the functions that the code has? The file has. There are 2 functions: sum and main. Main is mandatory. It might compile without a main, but it will throw an error like the main function is missing. So there are 2 functions in this particular thing: sum and main. So the sum function code, assembly code, TLS code will start at label 1. So we have label 1, and this is the translation of that particular any code. What are the parameters that are passed to this function? A. The type in. What is the scope of that? Like each and every open and closed parenthesis is identified uniquely by a scope. So you understand that, so there are 10 pairs of open and closed parentheses. There are 10 scopes. So why scopes? What is the need for the scopes? You'll understand. Like when you write for loop, inner for loops, like you might have know this. You can declare a global variable with I, and then use it again. You can declare another global variable with the same name I inside the for loop. But when you access it, it will access the local one, or one that is declared at the highest level, not at the lowest level. When you print I, you will print what inner part, like the global variable is I equals to 10, and inside an if loop you declared another variable and made it I equals to 20, And when you print I, you'll get 20, not 10, because when there's an ambiguity and it resolves by using the highest scope. So in those cases, scope will be useful. Scope will also be useful when for you to destroy variables. When you come out of scope and whatever variables that are declared inside that scope, you can remove that. You can use this scope variable for effective restore location and temporary code writing. You can use that. You use that and you can do that also. And what are the temporary variables that we are declared? There are no local variables. We didn't declare any local variables in the function. We just written a plus b. That's it. And the temporary variables, we differentiate temporary variables from real variables by underscore. So if some variable starts with underscore, then it's a temporary variable. So we name temporary variables numerically T1, T2, T3, T4. So this is the code. So the sum function got translated to these 3 lines of code. One is the address where it starts, and the assignment a plus b is getting assigned to some temporary variable, and we are returning the temporary variable. This is the tree address code. So we are addressing 3 variables. Here we are addressing only one, at max 3 variables, 3 address code. Yes. And the main function. So the main function got translated to this big code. Label to we have so 10 is getting assigned to some temporary variable, and that temporary variable is getting assigned to I. Why not just I equals to 10? When you compile, so this is the more generalized way of compiling. You first assign a constant to a temporary variable, and then assign that temporary, and then use the temporary wherever needed. So again, we are assigning 20 to some other temporary variable, new temporary variable T3, and then assigning it to J, and then we are interpreting that a function call is going to happen. What is a function call? Will happen to what function? Sum. So sum, each function is identified uniquely, so there will be no ambiguity. So we are calling sum. But if you built a very good compiler that compiles multiple files together, then you should have much better mechanism for identifying duplicate functions. And we are passing the parameters in order as they appear in the function. We are first passing I, we first pass J, and then we are calling. Look, okay, so the function that I'm going to call is sum, and the parameters are these 2. And to execute that function, you go to label 1. That's what this is saying, call label 1. Because label 1 is the label that we gave to this function. Each function will have its own label, starting point, like where does this function's code starts. And then after this, you return to label 3. In this label 3, you assign it to a new temporary variable, the return value, whatever returned by this function call, you'll assign that to T4, label 3 T4. And then this T4, you assign it to K. Again, the return value you return. So this is how it gets translated. So again, you see there are temporary variables, 4 temporary variables, and temporary variables also have scope. And this pointer will tell whether it is a pointer or not, yes or no. Like if it is a pointer, like what level pointer it is, with 1 star or 2 stars, 3 stars. That is like since we didn't use anything, it's not printing anything. In the local variables I, J, K, there are no parameters. Main doesn't take any parameter, and the return value is int. What is the type of the return value? Int. Again, same. This is what the compiler's job is. You can equally compile the complete OS. There are some errors, I think. I got to see some errors. There are warnings. Okay, assigning capping. So you can see there are some warnings. So the capability of the compiler is that how well is it easy for the OS designer to build that. So the OS designer, like the OS, whoever writes OS, by some mistake missed something. By mistake, if the compiler couldn't pinpoint that, it cannot identify that, whether giving a warning or error, then that error will go all the way down to the processor level, and we cannot debug there. It's very, very difficult to debug this project. The biggest challenges, there are 2 biggest challenges in this project mainly, not 2, 3 biggest challenges in this project. One is debugging. The first one is debugging, the hardest part. You don't know, even if 1 0 turns to 0, even if one wire is detached, even there is a delay or some kind of race condition happening in some part of the processor, if there is some delay in the memory accessing, or some one bit error, or like just 0 1 flipping in the assembler. If the assembler like it should actually assemble to 110, but it did 101, something like that. It will be very difficult for you to pinpoint that error, and it's going to take a lot of time. So make sure that each component is as much responsive as possible to errors. So for ease of programming. So there are many warnings which I ignored. Again, assigning char to it. I'm assigning some point of the voice. I am assigning a char to integer. That's the error. That's the warning at line 32. So this is also show the powerful, like how powerful the compiler is, how well it can show warnings, and also how well it can keep on compiling even though there are multiple warnings. That's what I think Dr. Ramana suggested when we did our project. Like our compiler at that time, when we showed Mitsun, on the first error the compilation stops and it reports. But it's much more easy if all the errors and warnings as much as possible gets detected only at one compilation, so the programmer can fix all the errors once and then compile again, instead of keep on doing like fix one error and then compile, because you don't know what are the other errors. The new error will come up, you fix that. Instead of that, try to continue with compilation, accumulate all the warnings and errors, and then show them at last. So there are attributes. So there are this many attributes. You saw all those global variables, voice variables, constants. There are no constants. I think if some point if I get constants, there are no constants there. So there are functions. Get char function, the strln function, clear shell function. There are many functions. So this main function. So there are many temporary variables. There are at least 31320 temporary variables. 1300 temporary variables generated. Too much. So that's also one optimization. How well can you limit the number of temporary variables usage? At least you can do that. You can think of doing that. Go to. So this all this is the temporary code. You see different kinds of code. If this is some kind of, so if temporary variables equals 0, go to label it. So this is one kind of you are addressing three things. 1, 2, 3. Make sure that it's not, the temporary code is meant for simplicity. Don't make it too complex. As simple as possible. Function call parse command. Call this is the label of parse command. Label must return value. So this is what I think. I'll stop the video at this point. I'll share the next video. I'll take rest and then start with the next video and then begin again, continue with translator. Thank you.